In this video, I'm going to teach you about significant figures, what they are, and how to count the amount of sig figs in a given value. To start, we need to talk about exact numbers. And if you can't tell from the name, an exact number is a number that is always exact. Some examples of exact numbers are any defined number. So for instance, 1 dozen is equal to 12 of something. A dozen is not a measurement like inches and centimeters are. It's more of a defined number. A dozen is always going to be 12 of something, okay? Likewise, when we get to dimensional analysis, conversion factors are made up of defined numbers. There are 12 inches in a foot. There are 5,280 feet in a mile. Those are defined numbers. An exact number could also be the result of a count. So if you look at the picture on the screen, if we count how many crayons there are, you can count that there are 8 of them. And there is no uncertainty that there are 8 crayons in that picture. So therefore, because there is no uncertainty, that makes it an exact number. Likewise, if we jump back to the defined numbers, there is no uncertainty that a dozen equals 12. There is no uncertainty that there are 12 inches in a foot. There is no uncertainty as to how many feet are in a mile or how many miles are in a kilometer. Those are all exact numbers. So when you use an exact number in a calculation, it is not going to affect the precision of your calculation. Other measurements will. Measurements are going to affect the precision of your calculations because they are always going to hold some level of uncertainty. There's always going to be some level of uncertainty in every single measurement that you make due to the instruments that we use. So when we are going to use a measurement in a calculation, we only use the numbers of significance. We don't go beyond the numbers of significance. And I'm going to teach you how to correctly do that on a graduated cylinder in the next slide. But before we get to that, we first need to review how to read the water level in a graduated cylinder. So you should remember that when water is poured into a container, it is going to adhere. The water in it is going to adhere to the sides of the container that you pour it into, pulling it up a little bit and forming this divot, also known as a meniscus. When you take a reading, we are going to take that reading from the bottom of the meniscus, not from the top. So it's really a great practice to get down to eye level with the bottom of the meniscus in order to take that measurement. Okay, so just keep that in mind when we get into the next slide. Now, when we are taking measurements, like I'm going to show you on these 2 graduated cylinders, you are going to report all the known digits plus 1 estimated digit. So for instance, we are going to look at this left graduated cylinder first. Now you see that there are marks on it, right? We have this line as 1, and this line as 2, this line as 3. Therefore, this middle line is going to represent 2.5, and this middle line will represent 1.5, okay? Those are known, they are provided for us. So therefore, we know that each of these little lines here is going to represent the tenths place. So this line is going to represent 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, and 2.7. So we know the ones place and we know the tenths place using this graduated cylinder. So therefore, when we report the volume of water in this graduated cylinder, we can report the ones place for certain, right? We know that this is between 2 and 3, but it's at least 2, right? And we can report the tenths place. So this line is between 2.6 and 2.7, so it's at least 2.6. 2 and 6 are known digits because they are provided by the markings on the graduated cylinder. So those are automatically going to be reported because they are certain. Now, we can't go any further with certain digits because there are no more markings on this graduated cylinder. So we get to add an estimated one. So we get to estimate the hundredths place based on what we think this line would be at. So this bottom of the meniscus here kind of looks like it's between 2.6 and 2.7, like right in between. So I might estimate the hundredths place to be a 5. So I could report the volume of water from this graduated cylinder as 2.65. The 2 and the 6 are certain, and the 5 is an estimate. That is a proper reading. Now, balances do this for you. So whenever you put something on a balance to find the mass of it, all of the numbers that are given to you are going to be significant. They are certain. So there are rules for counting the number of sig figs in a value, okay? So the first rule when determining the number of significant figures in a value is that all non-zero digits are always going to be significant. So all of the 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, those are always going to be significant no matter what, okay? So for instance, if I have a value of 9.6, since both of these numbers are non-zero digits, they're both significant. So I would report this value as having 2 sig figs. Okay, and sig fig is an abbreviation of significant figure. The number 145,285, all of these digits are non-zero digits, so therefore each and every one of them is significant. So I would report this as having 1, 2, 3, 4, 5, 6 sig figs. The second rule is that any zeros that are between two non-zero digits are going to be significant, always. So for instance, if we have the number 908, you know from rule number 1 that the 9 and the 8 are both significant because they are non-zero digits. Therefore, the 0 that is in between them, this rule is telling you, is also significant. So this number, 908, would have 1, 2, 3 significant figures. For the number 1005, you know that the 1 and the 5 are significant because they are non-zero digits from rule number 1. So therefore, the 2 zeros that are located between them are automatically significant. So that would have, that would make this number have 4 sig figs. The third rule is that a final 0 or any trailing zeros after a non-zero digit in the decimal are going to be significant, always. So we are just looking at these trailing zeros that are located after a non-zero digit. So all of the zeros that come after that in a decimal are going to be significant. So the 0 after the 4 is going to be significant, but these zeros before it are not. These are not being talked about in this rule. They're not significant. In this number here, the 3 zeros after the 8 are going to be significant, but all of the zeros before it will not be. Now, there are other types of zeros that we need to talk about, right? So I'm just going to briefly touch on why these zeros before the non-zero digit after the decimal are not significant. So these zeros in blue are not significant because we call these placeholder zeros. These zeros have to be where they are in order for the 4 and the 0 and the 2 and the 5 and the 0 to be in the correct places, right? If we didn't have these zeros, this number would not be the same as it is, okay? So these are just kind of like necessary. You have to have them, so therefore they are not significant. You don't have to have the 0 here, but you do, right? So that makes this 0 significant. The next type of 0 that I'm going to talk about are trailing zeros in a whole number. So if we look at the number 200, the 2 here is significant because it is a non-zero digit. It says rule number 1. The zeros after it are not significant because we also call these placeholder zeros. They have to be there in order to make this number 200. Okay, so this would only have one sig fig, and that's the 2. For the number 25,000, 2 and 5 are both significant because they are non-zero digits. However, these 3 zeros following them are not significant because, again, they are placeholders. They have to be here in order to make this number 25,000. So therefore, they are not significant. So this one, 25,000 would only have 2 sig figs. However, if you put a decimal after the zeros, so 200 and then the decimal, this decimal automatically makes those zeros significant. Likewise with 25,000, if you put the decimal after the zeros, it makes the zeros that come before it significant, but only if the decimal is there. If you have a whole number like this with zeros, the best way to report it is in scientific notation. You are going to report the number of significant figures in your value in the coefficient. We are going to use the number 100 as an example. If your value of 100 only has one significant figure, if only the 1 is significant, you would report that in scientific notation as this top one, 1 times 10 to the second. You're going to look at the coefficient. If the coefficient only has one value in it, that means that there's only going to be one significant figure. If I'm going to report the number 100 and it has two significant figures, I would report it like this. Okay, 1.0 times 10 to the second. This is still 100 when you put it into standard form, but now with the added 0, this is showing that I have two significant figures in my value of 100. If my value of 100 has three significant figures, I would represent that like this, 1.00 times 10 to the second. With the added 0 here, now I have 1, 2, 3 digits in my coefficient, so that is telling someone that I have three significant figures in my value when put into standard form. And then this one, this is also times 10 to the second, but you can't see it behind my face. 1.000 times 10 to the second times 10 to the second would have 4 significant figures because the coefficient has 4 sig figs in it. So the number of digits in your coefficient, when a number is written in scientific notation, is equal to the amount of sig figs in that value, always. This is the last slide, and it's kind of seems stupid, right? But if you ever see like leading zeros before a whole number, so like these two zeros before 155, which we don't see a lot, but if you ever were to see that, please know that these zeros are not significant. Okay, those don't need to be there. I don't know who in their right mind writes the zeros there, but they are not significant, so they would not be counted. Okay, so this value here, only the 1, 5, and 5 are significant. The zeros are not. Okay, and those are the rules for significant figures.